Hello everyone, I'm high school physicist and welcome back to my channel. My motivation in creating this channel is to talk about some topics in physics for an audience at a high school level or above. Hopefully that this channel can tackle young generations to appreciate physics. To know more about this channel, please watch channel introduction in the link written in the description. Today I'm going to be talking about mathematical physics, which provides example on how physicists use some mathematical strategies to greatly simplify their calculations. As mathematical physics is very broad topic, we limit ourselves for the following topics. How physicists work with transformation with logarithm as an example. How physicists work with small numbers. How physicists work with contrast terms, and the conclusions. To follow this video, you need to have some physics or mathematical knowledge, which includes kinetic energy, logarithm, angle measurement in radians, trigonometric functions sine and tangent, mathematical function fx, and simple calculus differential. Now let us start with transformations. The essence of transformation is we have a physics problem which is hard or expensive to solve. Then we apply a transformation which makes the problem is easier or cheaper to solve. Finally, we apply the corresponding inverse transformation to obtain the solutions. A well-known solution is logarithm. Using a logarithm table and the calculation routes, we can calculate a to the power of b equals c using only multiplication, and we can calculate d times b equals f using only addition. So we are equipped with logarithm table. We can use it to calculate exponent, for example, y equals 2 to the power of 3. Converting 2 to its logarithm, we then need to perform only multiplication operation to calculate y, and multiplication is cheaper than exponent. The second example is y equals 2 times 3. Converting 2 and 3 to its logarithms, we then can perform only addition operation to calculate z, and addition is cheaper than multiplication. An advanced example is Laplace transformation to solve differential equation problems. We move on to the second topic, which is working with small numbers. If we encounter sine theta or tangent theta, and theta is assumed to be small angle in radians, then we can replace sine theta or tangent theta with just theta in radians. An example is 0.1 radian is roughly the same as sine 0.1 or tangent 0.1. So we can simplify 2x times sine x into 3x for small x. And here's the summary. Sine theta equal to tangent theta equal to theta in radian for small theta. An example for working with small numbers is pendulum. A pendulum is hanging on the ceiling and oscillate with the maximum oscillation angle of theta. The equation of motion is then d2 theta over dt squared plus sine theta equals 0. As it contains sine, the solution will be rather difficult. So we can assume theta is a small angle, and then sine theta equals theta. Thus the equation now looks simpler. d2 theta over dt squared plus theta equals 0. And the solution is theta equals sine t. We now compare the solutions for the pendulum problem with sine theta, the blue curve, and with its approximation, theta, which is red curve. We see that on the left graph, that the approximation doesn't work for large theta such as 1 radian, but it works fine when theta is relatively small, for example 0.1 radian. The third topic is working with two contrast terms, 1 plus small number. We can take advantage of two contrast terms 1 plus x with x less than 1 for the following mathematical expression 1 plus x squared. For small x, 1 plus x squared can be approximated using 1 plus 2x. For example, for x equals 0.02, the exact answer is 1.0404, which is close to the approximation, which is 1.04. The second example is square root of 1 plus x. For small x, square root of 1 plus x can be approximated using 1 plus x over 2. An example for x equals 0.02. Again, the exact answer is close to the approximated answer. And the summary is a real example in physics is kinetic energy. The formula shows relativistic kinetic energy as a function of speed of particle. We assume that the speed of light equals to 1. We can then rewrite the equation into exponent form. For v less than 1, we can approximate the second term in the bracket into v squared divided by 2. And the final result is the non-relativistic kinetic energy formula that is familiar to us, that is half mv squared. Here are the plots of relativistic kinetic energy and non-relativistic kinetic energy. It is clearly seen that these two functions nearly coincide at v less than 0.3. Our last topic is working with contrast terms 1 plus large number. For large x, x plus 1 is roughly equal to x minus 1 or x, and also 1 over x plus 1 is nearly the same as 1 over x minus 1 or 1 over x. And for x equal 1000, we see those three numbers are nearly the same. And this is the summary. An example for the last topic is the distribution function fx in statistical physics. Distribution function is a function that weighs other function based on a parameter. For our case, the parameter is x. It is like probability. If the distribution function at x is a large number, it means that the probability at x is also large. In statistical physics, there are three well-known distribution functions. Those are Fermi-Dirac, Bose-Einstein, and Maxwell-Boltzmann. Fermi-Dirac and Bose-Einstein belong to the law X. Those are in quantum physics domain, while Maxwell-Boltzmann belongs to higher X, and it is in classical physics domain. Now we plot those three distribution functions. We see in law X, the function f splits into three curves. F Bose-Einstein is large, shows that the particle have more chance to sit at the same x. This is the property of boson particle. While F Fermi-Dirac is small, shows that the particle have less chance to sit at the same x. And this is exactly the property of fermion particle. At high x, these three curves nearly coincide with one another, which is the reason that we can safely use F Maxwell-Boltzmann, which is easier to compute. In conclusions, we showed 4 cases of mathematical methods that are usually used by physicists. The first is transformations. Transformations enable mathematics operation be done more easily and in lower computational cost. An example is logarithm. The second is working with small numbers theta, exemplified by sin theta equals tangent theta equals theta, and we illustrated a case of pendulum. Third is working with contrast terms, which are 1 and a small number. We illustrated a kinetic energy calculation in relativistic physics. Last, working with contrast terms, which are 1 and a big number. and be illustrated with distribution functions in statistical physics. Again, I want to thank my fellow Dark Calligraph as my internet technical consultant. If you enjoyed this video, please consider subscribing and leaving a like to support this high school physicist channel. See you next time and thanks for watching.